Good afternoon, everybody. So we shall continue a little bit further on this discussion on line coding or baseband shape manipulation. So here, initially, we have discussed some of the codes defining various types of 1-0 states can manipulate the bandwidth requirement pattern, just like non-return zero polar is this one, unipolar is this, and bipolar is this, Manchester coding. It is also possible to manipulate the pulse waveform. So for that purpose, there was some sampling by Nyquist criterion has been introduced. So the idea is to have distortion-less sampling. Now, what is the idea? The idea is that if we have a rectangular pulse, then if PT is rectangle, then of course we have its Fourier transform is a sinc waveform. Okay, so therefore this will have a side lobe. Now Nyquist argued that if we instead have a sinc waveform, like ideal this form, this is a sinc waveform of PT, then we will have the ideal bandwidth. So that means for this PT, we will have if we plot in the normalized frequency domain, normalized by the bandwidth, and the magnitude is also normalized. So therefore this 2B0 term will be normalized and we will have unit amplitude of frequency for a unit band. So this is the ideal impulse response that is desired for having zero ISI, intersymbol interference, because this is perfectly compact within the prescribed bandwidth. So therefore there is no interference between the adjacent symbols.
So why is it called an impulse response? Like, so here we don't.
Yeah, because PT we are taking as an impulse. Okay, this PT is the impulse. If we take PT, again, if we take the normalized time domain, T by TB, TB is the bit period. So ideal impulse response means it is the frequency response of the impulse function, PT. So ideal impulse response in the frequency domain. So it is, I mean, of course, generally by impulse response, we refer to the time domain response, either Hn or Ht. So or maybe we should write the frequency response of the impulse function. So ideal frequency response. Corresponding to PT. Now, because we require one sample in noise-free cases, ideally this should be symmetric. Okay. So in the noise-free cases, we require one sample. So the idea of the sampling is that we will take one sample of PT here, okay, and the sampling rate will be TB. So all others will be falling on 0. This is the sampling instance. So corresponding to various signaling schemes that we have seen, that there would be either PT will be modulated by AK. Okay, so AK is +1, -1 for various kind of schemes. So therefore, there will be either PT or no PT. So we have to recognize that whether PT is there. So for noise-free cases, sampling at TB at the rate of 1 by TB will produce only one non-zero value. Okay. So because it is this function, if it could be realized in practice, this is a sync waveform going from -infinity to +infinity. Now, since we are sampling at the rate of TB, so only one non-zero sample we will get in noise-free cases. Of course, if in presence of noise, this is no longer valid. So there will be shift of this PT, as well as there will be modification of the corresponding spectrum. But for noise-free cases, it is possible that if we have a design PT like this, then we could choose a sampling rate TB. Okay. Of course, it has to be exactly at the integer multiples of TB. Then only we will get the zeros. If there is, in fact, a variation in the sampling instance, suppose there would be always some uncertainty over this sampling period. The ideal sampler is a delta sampler. For the ideal sampler, we can have this been realized and noise-free cases. However, for practical sampler, this won't be possible because there will be an uncertainty of delta t on the sampling instant. Finite time is required to sample the value. So therefore, it is not practically realizable. Also, this PT has to be infinite long sequence. since we cannot design a filter, there are two aspects. Neither that we can sample at a particularly at an instant like an ideal delta sampler. Neither we can realize a filter to pass the box function such that the filter response will be perfectly like a box. Actually, we have a oscillator so which is generating square wave, so we have to manipulate with a filter such that we generate this waveform. Now that filter has to have a response like this ideal box function, which is again also not realizable. And second, there would be always a sampling uncertainty of delta t which is greater than 0. So because of these two reasons, this is not realizable. So practical solution is to smooth the box function. So practical solution for a finite band PF is to approximate the fall off to the stop band by an appropriate smooth function. So which will basically gradually decay. So there are various kind of functions which people have proposed, many kind of functions. One of them is raised cosine function. Various way it is possible, even it is possible by Gaussian function as well, because we know that the Fourier transform of a Gaussian waveform is a exponential complex multiplied by a complex exponential will give rise to another exponential function that is also Gaussian in nature. Of course, its sigma will vary. So according to some uncertainty rules, the sigma will vary, but the nature will be Gaussian. Unlike, say, box functions or any other functions where abrupt truncation gives rise to some distribution of the energy over the entire frequency domain. In case of Gaussian function, the distribution of energy is kind of limited both in time and frequency. So that also been proposed afterwards, but here we will just see what is the classical approach, that is the raised cosine function. So this is a function where it is defined by a constant 1 by 2b0 if mod f is less than a frequency f1. It is given by a smooth function 1 by 4b0 into 1 plus cosine pi mod f minus f1 divided by 2b0 minus 2f1. And 0 otherwise. So it is, of course, not ideal smooth function like Gaussian waveform, but we can call it a semi-smooth function.
So what is the condition for the middle value 1 by 4b0?
What is the condition?
Like so for mod f less than f1, it is 1 by 2b0, and 0
Yes,
for f less than this one. Like, what is the condition for the middle
because
value?
here we have 1 plus cosine is coming. So in case it is becoming 1, so in that case it will be 1 by 2b0. So the endpoints boundary conditions are matched. Okay, so that is that. However, there are other polynomials. I think there are other filter polynomials which can have attenuation function like inverse polynomial, etc. Those who will study filter, they will know afterwards. Like we have Butterworth smooth polynomial and other kind of polynomial which can also be used for designing such kind of filters. Now f1 and v0, that is the bandwidth, how to choose f1. They are related by a parameter which is a control parameter alpha, that is 1 minus f1 by v0. So usually our ideal filter was like this. This is f by v0, v0 f. I think v0 f, no, 42 is right, f by v0. So this is one, and then we have for certain value like alpha equal to half. It will come almost 0 at 3/2. It will touch 0 at 3/2. Sorry. So this is alpha equal to half, and this one is alpha equal to 0. So alpha equal to 0 means f1 by b naught equal to 1. So therefore 2 b naught minus f1. So that will start from 0 itself. Correspondingly, we have the sync waveform is modified.
For alpha equal to 0, like this will go from like at b0 it will just fall, right? So
Oh, sorry. This is not alpha equal to 0. Alpha equal to 0 is this original one.
yeah.
Alpha equal to 1. Alpha equal to 1 would be this. So then this will be f1 would be 0. Correspondingly, our PT, that waveform, that will be modifying. So alpha equal to 0 is this. Again, we have
Plane alpha equal to half.
so it is like this. Now this is alpha equal to half. I think drawing is not good. And for alpha equal to 1, sorry, not this serve, it will be little. So for alpha equal to 1, of course, there is an extra oscillation is coming into picture. However, because our sampling is at integer multiple of TB, so therefore these oscillations will not affect in practice. Though, as I, yes.
What is the right diagram? So what is it, sir?
The right diagram is the pulse waveform PT. I mean, both sides it is symmetric. So corresponding to this, the inverse Fourier transform, if we take this transfer function, the waveforms are modified like this. Say for alpha equal to half, it is still smooth like the sinc waveform, but it is little flattened. So this side is flattened little bit. And then if we have alpha equal to half, it is flattened not this much, a little bit more flattened. But the consequence is that there is one more oscillations coming to picture, extra oscillations, as the time increases.
Sir, for alpha equals to half, how are we getting the intersection at 3/2? I mean, how is it becoming 0 at 3/2?
Alpha equal to half. Yeah, alpha equal to half means that is half equal to 1 minus f1 by b0. So f1 by b0 equal to half. Okay, so f1 equal to b0 by 2. So f1 by b0 is equal to half. So this is equal to half actually. So at this, for f not equal to less than f1, so we have pf equal to 1 by 2 b0. Okay. So in case this value is normalized with 2b0. Okay. So this is 2b0 pf. So therefore, this for alpha equal to half, up to this point, this remains as 1 according to this function. Okay, and then we have this as it greater than f1, then this function is implemented 1 by v0, which is a smoothly decaying functions. And then what would be at 3/2, alpha equal to 3/2. One minus b0. Okay, so f1 by b0 equal to minus half. So f1 equal to
So could you explain the PT, so how it changes with alpha? Like for alpha equal to 1, it's just the sinc function, right? So,
yes, this is the sinc function. Yeah.
so if alpha equal to 0, it's a sinc function. Then so for the others, could you like draw it so I couldn't see which one is which? So.
No, one is still a smooth function. Okay, having only 2 zero crossings in this domain. So zero crossings remain same for the alpha equal to half. However, when alpha equal to 1, okay, the zero crossings, there are extra zero crossings coming into picture. Because from the 0 only this cosine modulation have come. So that will create extra zero crossings. For alpha equal to 1. For alpha equal to 1, this term is no longer there. Because from this 0 frequency, from that place only we have this function 1 plus cosine phi f minus f1 to be 0 minus f1. So f1 equal to minus b0 by 2. So therefore this will be say pi into f. This is f minus f1. So in effect, this is mod f plus b0 by 2. So therefore, it will have this 0 coming at plus half. Okay. So there are, of course, pulse waveform. Usually, the basic idea is to use a smooth filter, and corresponding to a filter, we have a generated PT. The desirable thing is that there would be at least some zero crossing at the sampling instance. These are the sampling instance. And there should not be any other zero crossing just nearby. So even if we have a sampling uncertainty of delta t, it should not be too near. So even alpha equal to 1, so that is not very near. So even if there is an uncertainty of sampling instant delta t, it may not give rise to a non-zero, positive value.
But sir, in that case, it might happen that it doesn't sample the exact zero. So
Yes.
then won't that be error?
No, the basic condition is that at the sampling instant, there should be a zero crossing. So that basic condition is satisfied by both these filters. So that is, but then there could be uncertainty of the sampling time of delta t, and due to that, some non-idealities will come into picture. So if that could be limited to a small value, that delta t, then those that may not affect severely, unless of course there is noise. In presence of noise, all these assumptions will need to be offset by choosing appropriate threshold. That has to be chosen again based on some detector performance estimation, and where we have to estimate the signal to noise ratio, the kind of receiver that we use. So at the receiver, there will be a filter. So that filter function will determine what could be the final output. So usually that filter function, in ideal cases, it will be same like the filter function that we have used to generate these pulse wave from PT. So general practice is that is again a convention, not convention, it is logical that because I have generated this pulse function by passing through a filter, then the value I will get correctly if we at the receiver pass through the same filter, so that the basic pulse waveform will be remain intact. So, however, in case of noise, there will be shift, and then we have to optimize with respect to the noise power, what kind of threshold we should choose. So that we may discuss a little bit afterwards, that when we will discuss receiver characteristics. So however, for this part, for baseband shaping, these are the some of the main idea. There are other, of course, schemes are there, those we will not discuss. There are other scheme at the baseband level. To manipulate the bandwidth requirement.
So if we use this kind of PT, then our that PSD which you're plotting, that will be more like a blue box, right?
No, PT is not box. PT is a sync function.
Yes, I'm saying so that if we use these kind of pulses instead of the previous one we used.
Instead of the box function, because suppose we have PT like a box function, this was the PT. Invariably, it is getting passed through a filter, like because our channel is a band limitation filter due to various requirement, because we have to multiplex several signals, several sources together. We cannot allocate bandwidth, use bandwidth to a particular user, so we have to limit the bandwidth. So therefore, it will be ultimately limited. Bandwidth allocated to a particular source will be limited. So therefore, that bandwidth limitation, if we have ideal bandwidth limitation, so like this will have a transform, again the reverse case. We will have a sync waveform and the frequency if this is the time. Okay. So then here, if I put ideal bandwidth limitation by a square, pass it through that, so this is the limit, band limit. Okay. Then the resultant will be that if we pass it and then if you reconstruct PT, so the PT will be noisy. No longer it will be that ideal one, but there will be noisy. So it will be something like that. So this will be beta T. Okay. So because of this, there will be problem. So to do that, manipulate that PT such that this band limit condition is satisfied. So that was the original idea. Of course, there are other schemes at the baseband to manipulate the bandwidth requirement. One of the important is, for example, correlative coding. Differential coding, etc. So many other schemes have been devised over time to make bandwidth requirement limited. So like correlative coding, I think today we can start a new topic. Or so correlative coding, we will not discuss in detail, just maybe the concept we will discuss, because we have to go to our next topic, that is modulation, and that we are supposed to complete before mid-semester. So correlative coding, just the basic concept I will discuss. So here the idea of correlating coding is that we have the signal, then we have a delay of TB, and then these two are input binary. So there is a unit delay of say TB, and then they can be summed or subtraction, whatever it is. Then this is passed through the channel. And of course, on the other side, we have a receiver, which can be a sampler at that instance. Now, what is the purpose of delay and summation? The delay and summation is that if we have binary values like 1, 1 are coming consecutively, because we have given unit delay, so therefore they will be summed together. Or in case of polar signal, so input values are distributed, say AK minus AK for 1 and 0 for 0. So therefore the delay will map it to a different values. There could be, if it is 2 consecutive ones are there, then that could become 0. And of course, if it is not there, then that could be AK. So that way we can manipulate it, the kind of, so this is called correlative coding, because by doing this summation, essentially we are introducing some kind of correlation. We will not discuss further, but this is again to manipulate the bandwidth of the signal. And because we have, we know that we have basically summed these two signals with a delay and the symbol mapping. So the output symbol, of course, can also be mapped corresponding to AK symbol, input symbol easily. So that way it can work. I mean, it can be interpreted as a, we are generating not only symbols, there will be, of course, interpreted as a summation and subtraction, but more to the PT. So what will be PT? PT would be, say, we have we can interpret it that the correlated, this is the correlated pulse waveform.
Sir, how is this correlated pulse coming?
No, because these two are, because these two are summed up together. Okay, so that way it is coming.
But so then one should be a PAT only because one is getting delayed, but what about that T plus TB? How is that coming?
Yes. Yeah, it is like PAT plus PAT plus PAT minus TB. Okay, let me write PAT. PAT plus PAT minus TB. Okay. So it could be interpreted in that fashion that I was writing, but suppose what we have done TB delay, so PAT plus T minus TB. Now then PAF, then we have say PCF. If we take the Fourier transform, that will be PAF into 1 plus, it is a simple delay, so there will be a linear phase term, 1 plus exponential of minus j twice by f, ftb. So that if we evaluate its power, so it will be power of PAF into, okay, so this will be cosine twice by ftb minus sine of pi ftb plus 1 plus, okay, just write whatever is coming. Square root of 1 plus cosine twice by ftb.
I think it will be root 2, right, sir? Because you're adding 1 to a circle.
Yeah.
Will it be like root 2 or something?
Yes. So cosine twice by ftb plus 1. Yes, first plus 1 would be there. We could manipulate it. Then what will happen? Cosine plus square root of mod f 1 plus cosine exponential cosine twice by ftb plus 1. So one term, if we put cosine ftb, then what would be other term? We'll put a I think it would be like, I have to check it, most probably it is like this. If I put 1 plus cosine 2 ftb, what would be the other term? It would be mod of cosine pi ftb. There would be some other constants will be there. Okay, let me.
So it will be 2 cos pi ftb.
I think let me write it some constant k. Okay. It could be written like this. So now that means basically the original PAF is now getting modified by this function, and that has.
Yes, it will be 2 cos pi ftb. So.
Yeah, something will come. I have to check it.
It will be 2, sir, because like 1 plus cos 2 pi ftb, we can write as 2 cos square pi ftb, and root over of that will become 2 cos pi ftb.
Yeah, so just I am putting k that in effect, what is that the PAF is now getting correlated with its adjacent one, because we have this PCT coming from one PAT and one delayed version of that is another delayed PAT, and together we now we have a pulse spectrum modulated by a cosine function. So therefore, this one is called the correlated spectrum because the two spectrums have the contribution, two adjacent pulse spectrum has contributed to this PCF. So that's why that is called the correlated coding. This is also known duobinary coding, because it is called duobinary also. If you go through the book, probably you will find that this is also known as the duobinary coding or signaling scheme. It is also known as so this duobinary name is coming, which is coming from the mapping of the spectrum as well as the symbols. It is mapping of the spectrum because if we plot this PCF, if we plot this PCF, so then it will be, we shall see that it will be multiplied by a cosine function. So kind of bandwidth energy is halved in the principal band. So, and duo means doubling the band. So that's why this terminology duobinary is introduced. For example, we had that PAF equal to 1 for less than equal to, say, RB by 2, or 1 by 2 dB, 0 otherwise. This is the original, and this one, because it is cosine modulated, so this will be equal to, okay, so this term again I have to write. So this CF that is equal to 1, so this will be equal to 1, then this term I think that K will be 2.
And also, from outside will be 2, then outside the brackets it will be 2. So yeah, 2 cos pi FTB.
FTB, there will be exponential term is there because I am not writing mod. So exponential term will come. Exponential term is pi FTB. this is for mod f less than equal to 1 by 2 dB, and would be 0 otherwise. So this is the essential of correlative coding. So where like if we plot PCF, so what would it look like? PCF will be modulated by a cosine. So it was PAF is a square. This would be PAF. This is so sorry, this will be cosine, not like this. So this will be PCF. So I think next we shall discuss about carrier signaling. So till now we are in the baseband. Our next topic would be carrier signaling. And I have already announced the class test. I think you have all received the mail.